Okay, I think we'll get started. So welcome everybody to the second panel for today, both in person and online. Hello, my name is Gulai and I'm a DDA student working with Professor Ali Makawi at Harvard Center for Green Buildings and Cities. So I have been researching and working on implementing AI-driven solutions for smart buildings both in academia and in industry. So this session, we are going to focus on the optimization, control, optimization, operation of the building environment, and specifically with the involved complexity of buildings for reducing costs, improving energy efficiency, reducing carbon emission, improving grid stability, and of course, providing better and more comfortable, healthier environment for humans. With the latest advancements in machine learning, AI, large language models, how can we use data-driven approaches to better understand, control, and interact with the building environment? So we have three amazing speakers who research and implement these solutions to the building environment. We will have Professor Nan Ma, Assistant Professor of Architectural Engineering at Worcester Polytechnic Institute, Founding Director of the Laboratory for Healthy, Environmental, and Resilient Buildings, and Giorgia Goldfeder, PhD candidate at Columbia, student researcher at Google, and a member of the NSF AI Institute in Dynamic Systems. And first to speak now, Professor Giorgia Chinazzo, Assistant Professor, Department of Civil and Environmental Engineering at Northwestern, where she also served as the Director of the Architectural Engineering Design Program. She also leads the Controlled, Adaptive, and Responsive Environments Laboratory. Welcome, Giorgia.
Thank you very much for the introduction and for the invitation. It's very exciting to be here and discuss these important topics. So in these 15 minutes, I will give an overview, let's say, of the research that I do in my lab at the CARE laboratory. And specifically, I will focus on how we can move, or what at least I'm trying to do to move from smart to human-centric buildings, and in a way that we don't just focus on energy efficiency or resource efficiency, but also to the occupants, so to the end clients of our buildings. And this is to have solutions to a built environment that is healthier, adaptive, and also more equitable. So let me give a brief context to put my research into the biggest innovations that we are experiencing right now in the built environment. So today we've seen what is happening at the urban level. Now we're switching at the building level, so at a smaller scale. And even at this scale, we've seen recently in the past years that we've moved a lot to smart and intelligent buildings. But then in the practice, those optimizations happen at the system level. And we forget about occupants and people inside of it. So are we at the end optimizing building for the grid, or are we optimizing the buildings for the occupants? And we tend to forget that the energy in the first place is spent for people. If we weren't here, we wouldn't have lighting, we wouldn't have cooling, heating. And because of the very large amount of time that we spend indoors, we still have very high energy consumption in our buildings. So almost 40% of the total energy consumption, and also greenhouse gas emissions. This is the global, but if you go in cities like New York, that percentage goes up to 80% associated to buildings. And if we optimize for energy efficiency and resources, forgetting about occupants, it happens that we might end up with buildings that are not good for their people. And what do? We're humans, so we react. We behave in ways that it might be not so energy efficient. So for example, I've seen people turning on a heater in the summer because it was too cold inside the space, or opening a windows in the winter because it was too hot. So the original energy energy consumption, even if the building was supposed to be energy efficient, is even higher than what was expected. And so this is the energy inefficient loop that I always describe. We have energy use in the first place for occupant needs, but if needs are not met, then we have occupant behavior, and this energy use is even higher. And then I always say that even if we manage to reduce the amount of energy that the buildings are consuming, but still the indoor environment is not optimal, even that small amount of energy that we consume is a waste of energy. So, because we're not just talking about comfort anymore, this was a huge focus over the past years. Now we're talking about health and productivity. So we're seeing more and more how poor indoor conditions are leading to health conditions that are, for example, related to asthma, respiratory conditions for poor indoor air quality, or respiratory diseases and cardiovascular diseases for excess cold or heat. So right now we have this intertwined challenge in the built environment, because we have, on one hand, still very high environmental impact of our buildings while still not having the optimal indoor conditions. So they don't go, even if we spend still a lot of energy, we're still not producing the best buildings for us. And this obviously results in very high costs, high direct costs, because we're consuming more energy than we thought or we should, and also indirect energy associated to, for example, more use of the healthcare system or a loss of productivity. So the challenge is really to balance these two, so reduce the energy in our built environment while improving at the same time the indoor conditions. And this is what I'm trying to do every day with my group of students. And what I really think is that we need to envision a way how the smart building can be even smarter or more intelligent, but not just focusing on energy efficiency, but also considering humans. And what I mean by that is humans at the level of health and well-being, but also humans in the sense that everyone should be able to achieve or obtain the same treatment across different types of buildings. Because otherwise, just focusing on this one, we end up having buildings that on paper are very good, are high-performing buildings, but then in practice they might be alienating, unhealthy, and unequitable. So one important point of my research is that when I'm talking about human-centric environments, I'm not just talking about comfort, so I'm not just talking about avoiding discomfort, so avoiding glare, avoiding very hot and very cold spaces. But what I'm trying to do, or that's the ambition of my research, is to look at the positive effects of the built environment. So how can we have buildings that are actually enhancing the quality of life of people? For example, can we have buildings that are increasing our happiness or boosting our learning, improve how we sleep, even enhance how much we move or reduce our stress? And the vision is to achieve that through truly human-centric building design and operation. So those are buildings that should follow design principles that are based on human-centric models and design principles. And then during the operation phase, they're able to sense both people and the environment, and through new innovation technologies and AI-powered algorithm, are able to respond and adapt to occupant needs. So again, this is a vision. Are we close to that vision? Not really. We're still missing a lot of information to achieve that. In my research, I divide those two research gaps or knowledge gaps into two major buckets. So the first is fundamental knowledge lack. So we don't know what is now called human-building interaction. We still don't know a lot about how buildings are affecting humans and how humans are affecting buildings. And connected to this, we're missing theories, framework, and models that we can use. And then we're missing the link between theory and practice, basically. We're missing tools, methods, and technologies to make what we understand at the basic level actually practicable or relevant for people that are practicing architecture engineering. So this is a very broad field, and among the many things that we still know about the interaction between humans and building, I'm specifically focusing on multi-domain research. So that means that I'm looking at how domains interact and combine together, influencing different human responses. And what do I mean by domain, or at least what do people in my field mean by domain? Those are the indoor environmental qualities, so visual, thermal, acoustic, indoor air quality are domains, and they have different types of sub-factors within it. So the thermal obviously include air temperature, mean radiant temperature, relative humidity. Visual includes luminance, view out, and glare. But as part of a larger group of experts, we also expanded the domains to include the personal and the contextual factors. So for example, thinking about the work status of people or the socioeconomic status is looking at the personal domain, and in the contextual domain is looking at the climate, system design, or time of the year. And multi-domain research looks at how these different domains interact and combine together, influencing different types of human responses, ranging from perceptual to physiological, psychological, and behavioral. So, for example, I conducted the first experiment with the use of daylight, and to understand how daylight and temperature were interacting and combining together to influence different types of human responses. I investigated both daylight quantity and daylight color, quote unquote, because it means daylight passing through colored windows. And among the many results that I obtained in this set of experimental studies that I conducted into climate chamber, so a control study, I just wanted to highlight one example. So here, in this control experiment, I changed the temperature, and also I changed the quantity of daylight, so from dim to bright. And what I found was that the thermal comfort of people within the same temperature was actually affected by the quantity of daylight that they were experiencing. So in a cold room, people were more thermally comfortable if there was a lot of daylight, and the opposite was true in a warm room. So they were much more comfortable if the daylight was dim. And why that happened? I believe because expectations matter, or this is at least a theory I advanced about expectation. If you step into a very bright room, you would expect it to be also very hot. But if it's not hot, and it's actually colder, and it's also cold in a way that is out of the comfort zone, that might be perceived more thermally comfortable for you. So this is just an example to show how multi-domain research, despite being very fundamental, can lead to both increased human comfort and also energy savings if buildings are operated according to this kind of theories. So as I said, I'm looking a little bit beyond comfort right now. So this is a study that I'm currently pursuing with one of my PhD at Northwestern. I'm just showing here some results that we just presented at a CISBAT conference in Lausanne in September. What we did here was to study in some of the classrooms at Northwestern how people were feeling in terms of mood, stress, comfort level, and productivity, perceived productivity, and also how they were judging the air quality, light, noise, and temperature satisfaction. And then we tried to see if this response is correlated. So this is a pure perception study. What we saw is that if people were satisfied with air quality and temperature, their mood, comfort level, and productivity was also higher. But there was no correlation with the noise in this case. And also interesting, our students were stressed no matter what. Or not stressed. I mean, some people were not stressed. So stress was not correlated to that. And right now since we measured also the indoor environment, right now we're looking to see if the actual indoor conditions, so if the actual measurements are having the same effect on the mood. So instead of having temperature satisfaction here, we would have the actual temperature that we measured. And the end goal is to understand in a supposedly automated way to control the indoor environment to increase these parameters? Should we look at occupant feedback or should we look at measurements? And this is what we hope to find soon. In the context of the multi-domain studies, I've been very active at the international level, and I led a group of more than 70 experts to define guidelines and recommendations for multi-domain studies. Because what we observe is that, or at least that was very frustrating at the beginning of my PhD, so if you're frustrated in your PhD, don't worry. Everyone goes in that phase. But there was a lot of confusion about the literature, and there were a lot of contradicting results, and so I couldn't figure out what was happening. And then by going a little bit more in depth in these studies, I realized that there was a lot of discrepancies regarding the experimental design, how people were reporting the effects. So with these guidelines, we hope to provide some kind of guidance on which factors to consider when you run a multi-domain investigation, and also how to report it, which language to use to have a more uniform kind of results, so that in the future we will be able to conduct more meta-analysis, for example, because right now it's just very confusing, the field. So that was for the first bucket, let's say. In the second bucket, I'm looking more at tools, methods, and technologies. For example, I'm looking at how natural language processing are used to gather information from occupants beyond surveys. I'm looking a lot at new sensors and also how we can use existing sensors, how we can optimize their location inside spaces. And in new sensors, I'm looking at them for understanding how we can measure better the indoor environment, but also how we can control the indoor environment. So as part of this, I'm also looking at personalized comfort systems. There's no time, obviously, to go in all of this, so I just wanted to provide some information about the first bucket. I conducted a study where I scraped from the web more than 1 million online reviews from a website which is providing information about different workplaces. And among this online feedback, I was looking specifically at what people were saying about the indoor environment. And what I saw is that mostly people were complaining about thermal, both hot and cold environments at the same time. And they were also reporting that the thermal was the most bothering conditions in their work environment across different workplaces and across different locations in the US. That was a starting point for another study that I co-authored, where starting from the database I collected, I helped develop this IQ large language model that now is on a website. You can go there and you're going to have an interface where you can basically input any kind of text, and that will help you define which kind of complaint it is that text about. So if you say the classrooms get always very stuffy, you would say the model would say this is about indoor air quality, but the model is smart enough to say, obviously, that if something is not about IEQ, it detects it. So Harvard has great coffee machines, nothing about indoor environment. But if I say my colleagues are very cool, even if there's the cool word, the models detects the context, and it says this is not about the IEQ environment. So this is, again, obviously a very initial stage, but the hope is that if we integrate these kind of tools and methods into the building system, the building automation system, we might be able to get information quicker, in a quicker way, and in a way that maybe people will feel less alienated than replying to questionnaire, and we might be able to act quicker. And to conclude, I just want to put the equity part of why I'm interested in equity. So in the web scraping study that I showed you before, what I've seen is that most of the complaints were coming from people outside of office settings. And most of the building science research is about office settings. Obviously, this depends on how easy it is to get to these places, but I think this highlights the need to go beyond what we're currently doing. So this is in terms of work status inequity. With a team of brilliant women, I also ran a study, a meta-analysis and review of past research on thermal comfort, where we confirmed with data, with a meta-analysis study, that actually women feel significantly colder than men in cold environments. And it also depends, like the thermal comfort on women specifically depends on the life stages of the women, depending on pregnancy. Right now, I should feel warmer, but I'm actually cold. But who knows what's happening right now. So this is all to say that for the equity research, we should include a broader population into our experiments, but also, if we're looking at the second bucket, we need to provide technologies and methods that are affordable for everyone. Because if we make these smart and intelligent buildings only for glass towers in Chicago or Dubai, we're not making any good for the whole community we're living in. So this is my take on this rethinking the building intelligence. That's this panel of today. And every day I'm trying to achieve it by doing research at the intersection. So I am by training an engineer, architectural engineering. So I always feel that I'm in between these two fields, engineering, so very tech-oriented, and architecture, so very design-oriented. And I also like to put this flower of knowledge in between. So I really think that to achieve this human-centric building, we need to add or consider building a lot of sciences. So building health, computer data, and social science together to really achieve this truly intelligent and human-centric buildings. And this is what I'm trying to do every day at CARE. And again, thank you for the invitation, and look forward for the rest of the presentations.
One quick question. When you talked about, I think, the perception and the discrepancy between different research that's happened in the past, I think this is a really interesting kind of segue to ask you, how about more evidence-based type of approaches? Do you have any insights on like the tools, the workflows that could be used to, analyze if these perceptions make sense or not?
Yes. So right now, I keep working at the international level, because I think that this should come not from an individual lab or from an individual person, but as part of a community. So right now I'm working in this Annex 95, which is the sequence of Annex 79. And we're also looking at how scales can be used across, like, how do you ask people how you feel? So if there is consistency across different studies, it's easier to find an agreement or to find similar conclusions. Right now, it's maybe because it's still a kind of a new field, we still have a lot of different responses, and it's hard to put together different types of studies together. So I think having a kind of standardizations or guidelines is really helping the field to move forward.
Sorry, for time's sake, save the question for the panel discussion later. And thank you so much, Giorgia.
Thank you, everyone.
And
Alrighty, I think the clock here has becomes negative, so I will try to ignore it. Thank you so much for having me here. Today I'm going to talk about how to leverage, generative AI, as a lot of attention recently we have been putting through into research world, how generative AI, specifically large language models, can help us to monitor even globally or regionally, and at the state level or regionally and national level, to help us to better understand the health and livability concerns and how we really optimize, the building responsibility to all those livability concerns that we could learn. So I would remind everybody that why we need buildings. And I think, to me, the major takeaway is we are just the direct services of the buildings, right? And that's really the buildings why exist, because we cannot adapt ourselves to extreme conditions outdoor. That's why we need all this HVAC system running for the people. But traditionally, right, the way that we understand whether the HVAC system or the HVAC services are providing the right way to the occupants is through survey and a lot of sensor measurements. And, a lot of questions around that is we basically wanted to know whether indoor environmental quality perform good for the people, or whether the energy and carbon footprints are doing the right thing with maintaining all the daily activities we're having for the building occupants. But it can be very costly and labor intensive if we're talking about very large scale, urban scale, or even state scale, nationwide survey or data collection. Is almost impossible. It's just going to cost a lot of labors and sensor deployments around that. But on the other side, we are also the primary influencers of building energy usage. There are tons of papers and studies available out there just saying like, look, this is the simulation results and this is the actual smart meter data, and there is something we call it as building performance gap. It is all because we are the active actuators of all these building systems. We kind of, interact with the lighting system, we interact with the blinds, we override the thermostat settings that if we feel not happy about it, we are just become the primary drivers of all this building energy usage uncertainties that we never can predict during building simulation or building energy modeling stage. But, on the other side, we are smart enough, right? We try to develop very intelligent, very smart sensors to replace humans, or sometimes they can stand in to sense something that humans cannot sense. But I have to acknowledge that we have been developing our biological system for over probably millions of years. We have to acknowledge that we probably are the most or the smartest or the most intelligent sensors we never develop in this planet. And we can be the sensors, right? We can leverage all the sensory systems we develop as we evolved as humans. And some of that, can be leveraged as part of, the sensor network or the sensor network development or the platform that we develop together. So we can work with the sensors, and sometimes, if the sensors cannot provide enough information, maybe, we can provide some of information that complement the sensor information that we cannot get. So I put a lot of attention into social media data, because I think, to me, that's the channel or the platform that I can hear to a lot of human voices, or the way that I could understand how people sense about their environments, because there are so many user-contributed actively or passively data that are available in social media, right? Like, we all have our mobile phones and we carry it with us almost every day. We, occasionally, or some of you guys pretty frequently posted something on social media and talking about, this troubles and that frustration, or even some kind of building, complaints. And how can we really leverage all this user-generated social media, right? So we don't have to deliver service basically one-to-one, but how can we really use all this user-contributed, no matter as passively or actively, through their social media platform. And I wanted to emphasize or highlight why it's so important, why I like social media data a lot, because to me, it's just open-ended, and there are massive, abundant big data available, and indeed, there are big textual data available out there. And if we deliver a questionnaire or any surveys, we have to predefine what questions we would deliver. So that, to me, is we kind of really think about what complaints or what dissatisfaction they might have. So we give that limitations, we set up that restrictions already, but through social media, it's gonna be open-ended. They can talk whatever they want to talk, and maybe we can get a lot of information that they talk about their buildings, and we can leverage that knowledge and gain a lot of insights and to understand how the buildings can be designed and operated better for the people. And again, they are not solicited. And many, human subject recruitments, we provide some kind of incentives to hopefully get some of the data. But, most of the social media data, they are not solid-stated. They just publish as the record for their daily activity. So I was like, okay, maybe we could get a lot of useful information by not setting up all those restrictions to what they have to talk about in their social media posts. And then it led me really to think about how can I really deal with all this massive tons data sets available on social platform in general. And if we look at the evolution of large language models, this is not the holistic map at all. This is the paper that I found, I believe, in 2023. We got a lot of new large language models recently, in recent 2 years, I guess. So this is not exhaustive map, but look, there are so many large language models available in the field, starting from so many big tech companies from Google and from Meta and from all those small startups that are trying to do something with large language models. And I really look into what really trained to make all those large language models available and what are those training data sets behind all those hyperparameters or model architecture they really come up. So we dive further and really look into that many the training data sets that used for training all those large language models are really from web pages, scientific data, or Wikipedia, or fictions, or some kind of books. Then I wonder, if we wanted to use all those large language models to help us diagnose all the social media data, all this textual data, to make sure that we can get the information that we are always interested in, which is building, right? Architecture or the building environment. Then how much I can trust with it, right? That's the question is, if we know that all those pre-trained large language models are not dedicated to the building field or do not have enough building domain information, then how can I really fine-tune or develop method that to make sure all those pre-trained large language models are trained based on the other data sets? It's not really about building, but can equipped with in-depth building domain knowledge. So what we did here is we scrapped extensively, mainly at this stage, or from Airbnb and Booking.com. We really look into the 60 major cities by population. We're not limited to the US. We're looking at the worldwide problems, and just say if we have tons of massive textual data available there, can we really get some kind of understanding of how people really sense about their environments? So overall, we got 22 million reviews from all those temporal residences, and then we really look into English posts because I wanted to make sure all those labels and classification process really make sense because I only can speak English very well, and also all those pre-trained large language models really can perform very well for English. So we try to limit to English written reviews right now. So that would limit us down to 13 million reviews. So what we did here, there are so many large language models out there, but we specifically pick up the one called BART. People are kind of debating whether it's super large enough or large enough can be called as large language models. I will get rid of that. But I think BART is a good large language model to get started. And I like it a lot because it comes with two components. The first part is the BART encoder, and the second part is GPT decoder. So that means if you try to train the whole algorithm, right, it's going to take a lot of computational, resources. So what we did is, if the encoder is not doing so much of work, then we can just work with the fine-tuning process optimization for the GPT decoder only. So what we did here is, as I said before, all those pre-trained large language models do not have any building knowledge. How can we do it? So basically, we develop something I call it as the vocabulary dictionary, which comes with all this information that I believe I could describe all those building environments better to the pre-trained large language models, and that comes with the dictionary that we can train and as the input layer to go GPT decoder. And then just make sure that any data that we try to deal with at the training process can be seen or can be learned over there, or maybe some of them are not available or in the training data dataset, so we add another classifier. It's called natural language inference classifier over there. So that means it just double make sure that if any label or any data that you're having in your training dataset do not actually repeat again in the validation dataset or testing dataset, it would make sure that it can understand human languages and what they describe in their buildings, because it can be very possible that people talk something and your model didn't see it in the training model, in the training dataset, but could be existing in the testing dataset. So we add another layer here to make sure that all this, zero-shot learning process can be learned through all this fine-tuning process. And then we created a loop here to let the model itself to be learning about all those training processes. And it's kind of typical, the fine-tuning process, that how we actually fine-tune all these hyperparameters in this architecture, and then becomes a loop to reduce the loss and optimize its performance in this case. And then we also look into, if we separate social media data, very long sentences or very long posts, into different sentences, right? It comes with a two-stage classification. We identify the problem from each sentence, but we also identify the problems as a whole if we give the complete post as, a classification label down there. And then we also, given that, we also try to know how people really satisfied or how dissatisfied about those whole buildings, or if they talk about anything that could express their environmental opinions, what will be their environmental preferences or environmental expectations while they're inside the buildings. So I wouldn't spend a lot of time here talking very specific details about all those findings I have, but I wanted to just show you that the preliminary results that we get here across the globe, that you can tell there are so many buildings across different regions of the world that facing very different concerns in terms of indoor air quality, in terms of thermal comfort, in terms of acoustic, and all those grades over there with the city as we try to geocode all those profiles and to understand at what location in what city has major problems for what major problem. So this is the whole map, combining multiple level of understandings of people really think about their built environments as the temporary residences as an example. And then beside that, we also try to understand, okay, if people are complaining a lot about overheating and overcooling, about indoor air quality, and how can we really implement that knowledge to building operation guidance. And I think the social media data does have that pathway and does have that potential to give us more information about learning the real environmental preferences, environmental expectations, and implement them into energy modeling and give us more operation guidance, because we can learn from so many building occupants in the nation or even across the world. And we also learned that there are so many information embedded in social media taxes that comes with all those, I call it temporal, spatial, and behavioral information. It also comes with how people interact with their buildings. For example, they talk about, I bought a new purifier, so I would assume if there is a wildfire happening or high air pollution days really come, then this person is very likely to, take the action or take the behavior on their air purifier. So it would give us lots of opportunities to learn from, where people they are, what activities they're taking. So I think, social media data really opens that opportunity around the building occupancy schedule and how really understand the building can be optimized for the people and what behaviors that they're taking there, because there are so many social media data comes with the geocoded or geospatial information out there. I just wanted to share something funny that you probably never thought about to learn from your survey or the questionnaire is we're really looking into some unique sources that the livability concerns that people throw there. There are something that I highlight, like for example, people complain about dog barking, kids, footsteps, fire alarm. And then we also learned that there are, almost 100, super negative reviews, particularly happened in Las Vegas, that people really talk about about indoor air quality as their major concern. I look really into all of this, their living experiences, and realize, all those, residences are close enough to the fish market, and that's where, all the smells and complaints about indoor air quality about. So I think, it's really time that we have to think about how to localize or how to tailor down the specific building operation guidelines, or the strategies to the specific context that they have to deal with. I wanted to have some kind of high-level, conclusion for my presentation today. Is I have been thinking that, we have been spending a lot of efforts in our field to build high-performance buildings, but I think we also need high-performance people in high-performance buildings. And how can we really incentivize them through all this rewarding system that we can think about as part of the integral, components in high-performance building design. And we developed the blockchain system and IoT sensors. It's all streaming data together and signing up the smart contracts so that we can get high-performance people incentivized and rewarded in all the sustainable building. And I think, a lot of research that we have been doing is to really advance infrastructure resilience, right? If our building itself is more resilient enough to all these extreme conditions, so we don't have to lock into all the options that heating and cooling services can only accommodate, but the building infrastructure that we all invested a lot could also build up our resilience to the climate change. And I kind of echoed to a lot of presentation that we heard about it today, that I think we have to do more with the cross-disciplinary research, and that's what I've been doing in my lab. That I got a lot of students from very different disciplines, and we all come together to think about what would be the integrated and holistic solutions that we can propose so that the buildings and the cities shouldn't be sacrificed a lot for the climate disasters or all these public health concerns we have to deal with. This is the last slide of my presentation. It's kind of the call to the action that, to me, I think the building has to be more occupant-centric. We have to listen to their voices. We have to respect their opinions. And we just need more data, more public available data for the field. We have to continuously develop new methods and new technology, because this is not intelligent enough world that we're living with. That's it for my presentation. Thank you so much for your attention.
One quick question, if there's anybody. One.
Thanks, Nancy, for the presentation. So since I also looked at the online reviews, do you think that the experience of people in these temporary places will be very different from their actual homes? And how can we get this experience from people in their homes through social media?
Yeah, so I think that's a lot of kind of like conversation I had with my students as well. Like, I feel like, this study that I showed today is really about the temporary residences or not, the permanent houses. And we really look into, the Twitter right now, we call it X, and Reddit and Facebook. And it honestly, it becomes weird if you are at home and posting something about your home. It sounds kind of weird. So I think my approach is try to understand the residences in general, that what would be the impression that you would have with the residences that you have to deal with. And hopefully that would shed some new light into, better understanding about how to operate their residential houses or how to operate, offices, which is not, the permanent spaces or the environment that you're always exposed to, but you try to have some kind of modifications and interactions with the buildings that you're not familiar with. Because I think, to me, like residential houses, you probably have kind of more routines and you know what you're really doing. And then if you can collect that data, then it's highly possible. And I try to really look into the buildings that could give us a lot of uncertainties and highly variable occupant profiles that it's very hard to model and predict at the design phase, and how can we really propose another methods to to get that uncertainty quantified better. Yeah.
Thank you, Nan. Thanks.
Hi, everyone. It's an honor to be here, and I'd like to thank the organizers for running such a well-run event. So I'm going to talk a bit about what to me is a very central question, which is, why are buildings lagging behind? We have AI advancing so many different industries, and yet, at least from my perspective, we have definitely very cutting-edge labs, but most buildings today are the same that they were 10, 20 years ago. And so that's going to be the question that I want to explore. And so first, let's just start with the motivations. Why, when we say that we can make a building more optimal, what exactly do we mean? And so I'm sure everyone knows these stats. I think they were actually said earlier today, but buildings consume about 30% of energy use, about 30% of carbon emissions, and it's only getting bigger and bigger. So there's an enormous incentive for us to optimize buildings. And then, I think it pays to get very concrete when we speak about optimizing buildings. What exactly are we optimizing? So there's a lot of different factors. We have, for example, most devices are only optimized locally, but they don't communicate globally, right? To give an example of this, you might have 100 VAVs in a building. They don't know about each other, right? They might be very, very optimal in their own local control loop, but they don't know about the state of each other. They can't interact at all. Obviously, outside weather is definitely kind of maybe even the most low-hanging fruit, right? Things like just the temperature forecast. I think there's basically, most buildings aren't taking into account if the temperature is going to rise, if it's going to fall, is it going to rain, all those sorts of things. Obviously, human occupancy, which was spoken about today, is another very important consideration. And then another thing that maybe people don't think about is also price varies throughout the day, right? So there's peak and off-peak hours, and so you want to have buildings that are using electricity when it's cheaper and also when it's more renewable. So these are kind of the main considerations. And the way in which we want to optimize it is reinforcement learning. So reinforcement learning, for those who aren't familiar, it's one of kind of the 3 pillars of AI today. Basically, it means learning from experience, right? So basically we have this environment, which in this case is the building. We have the agent, which in this case is the controller. And the agent learns by interacting with the environment how to run the environment more optimally. So that's kind of the paradigm that we want to do this. But I think a central question is, why now? What is kind of unique about where we are today? Why I think we're hopefully at some sort of inflection point towards the future. And so I want to start with a bit of an interesting timeline, if you will. So in 2016, DeepMind published a paper claiming that they could reduce data center costs by 40%. Okay? It's been about 9 years. All right, let's move forward a bit. 2018, they claimed they had also cracked data centers even further. In 2022, they moved on to commercial buildings. And so they've now claimed to have basically solved both these problems. Okay, let's fast forward to 2023, where somehow, despite claiming they've solved all these problems, they asked me and a few other people at Google to join and work on optimizing their own buildings. And so this confused me a lot. And I think it's actually getting to a very central point, which is there's so much research, decades really at this point, on using AI for buildings. They didn't call it AI maybe 10 years ago, but there's so much research on this topic, and yet it's not being used. Even the people that are claiming they've solved it haven't solved it. And so I think it's a very important point, and that kind of gets to the work that we're doing at Google, which is attempting to bridge this gap and figure out what's kind of gone wrong. And so I think there's probably a lot of different disconnects that are responsible for kind of what we just said, but I think perhaps the most central issue is so many of these systems are built on simulation, and they just don't work in the real world. And even the ones that do work in the real world, they work on one building, right? So maybe you have your simulator and you spent months and months getting it really, really specific and narrow, and now your simulator does transfer to your office building. Great, you've solved your problem, but you've not solved the problem for anybody else. And so the main focus of the work that we're doing at Google is to try to understand and explain, can we actually build building control systems that don't just work for one building, or even worse, 0 buildings, but actually work for everyone. And so reinforcement learning has a lot of very, very big challenges, right? So we mentioned we're doing trial and error, right? So you can kind of imagine a robot playing in a sandbox, trying to kind of figure out what it's doing. So you might not feel comfortable letting that just happen in your building. For example, maybe the AI needs to turn off the hot water, let the pipes freeze, and then it will learn, oh, I shouldn't do that. but I don't think you want that to happen, right? I think you kind of would want it to come baked into this knowledge. So reinforcement learning, learning by trial and error, is very expensive and often dangerous. It's also very slow. So these systems tend to be very, inefficient. So even if we could put in guardrails, right? And this would be very safe. Well, I can't exactly go to a building operator and tell them, okay, great, we're going to have this run your building in about 40 years. We'll tell you how you can run it more optimally. So how can we actually solve this, right? What are our approaches? So probably the simplest approach is to just look at offline data. By offline data, I simply mean you take a building, you have, let's say, some set of sensors, and you just look at all the data the building did in the last year. And then you just analyze the historical data, and you see, can we do better? The problem with this is you can't actually interact, right? This is just, the history. You can't actually test any counterfactuals. And so this does work, but you're only going to see, at best, 1-2% gains in efficiency because you're very limited to what you've observed. The second approach, which is very popular in the machine learning community, not so popular in the buildings community, is to actually just learn the dynamics. So basically, you take your historical data, you then build a machine learning model that should then understand the trends. The main issue with this is they don't actually incorporate any sort of physics. And so one of the big challenges in machine learning is, can you really generalize outside of the domain, right? You trained your model on a year of your historical data, but it doesn't really know what happens outside of the baseline policy. And then the third approach, and this is probably the most common, is using a simulator. The one you see the most is Energy Plus. Maybe some of you are familiar. And there's kind of a big trade-off here between how long it takes you to develop a simulator and how useful it is, right? I could spin up a simulator. It could take me 6 months to get the material and all the walls and the height of the ceiling and all the vents and all that stuff. So I spent 6 months. It's very expensive, and even then there still are lots of sim to real transfer issues. And so the question is there a better way? We can't just learn online, it's too dangerous. We can't just look at historical data, there's not enough variation. Learned models don't generalize well. Simulators are very hard to configure. And so the way that we want to do this is basically a combined approach. And this is what we're working on at Google, where we take a low fidelity simulator. And by low fidelity, I'll explain what that means more in a minute. But basically, we mean that it's very, very easy to configure. You could configure this in about, an hour, 2 hours for a building, but it's not that good, right? We then take data, and the goal is to use the data to calibrate the two together. It looks like some of the text is very small, but hopefully you get the idea. We're taking a lightweight physics model, combining it with data and machine learning, and hopefully then it bridges the gap. And so there's kind of this trade-off between fidelity and speed. By speed here, I mean speed of actually configuring and getting it running. So there's a lot of different debates. We kind of are hoping to find the optimal trade-off. I think it's still a big question of exactly where is this trade-off. But let's discuss a bit, now to get more technical. Hopefully now you have a high-level view of why we want to do this and what we're trying to solve. What exactly is our simulator? And so we're using a finite difference approximation. Basically, to say it in very, very simple terms, we take the building and we divide it up into rectangular grids, and then we use a first order approximation to calculate the thermal diffusion. This is very, very cheap. You can do this on a GPU. We can simulate basically an hour of building time basically in about a second. It's very, very quick to run this on a GPU. The downsides are we're basically making a lot of simplifying assumptions. And so that's kind of where the data comes in, hopefully to mitigate that and to make it work. The next question becomes, if we want to have a very, very rapidly configurable simulator, well, how do you actually get the building, the layout, right? And so one of the advantages, I mentioned that we divide the building up into a grid and we perform very basic thermal calculations. That actually makes the onboarding process very, very easy. So basically we can take like a regular floor plan and then we pre-process it to look like that. You can see this can be done very, very rapidly. And that is your floor plan, right? Because as I mentioned, we're just dividing it up into grids. You can just view every pixel, right, as kind of a control volume, and we're able to get this running on a new building, as I said, literally in an hour, 2 hours, very, very quick. And then the next, so this is kind of what it looks like. We go from a floor plan to a building very, very simply. But the next question becomes calibration. And I think this is the most important topic, because it's very nice if we have a very rapid simulator, right? And it's easy to configure, it runs quickly, but if it doesn't work, then no one's gonna care, right? And so how do we get it to work? How do we actually calibrate it to real data? So this is really a central question. And I think this is maybe still an open question, but I'll tell you what we did and kind of where we wanna go. So we take our historical data, and the goal basically is, can we find physical parameters of our simulator that match the historical data? Now, the problem with this is it's a massive search space, right? Because when we're just taking a floor plan, we don't really know anything, right? We don't know how thick the walls are. We don't know, airflow. We don't know so much, anything about materials, right? All unknown to us. And so it's a very, very high dimensional space. It's very difficult to actually figure it out from data. What we try to do is we use a hyperparameter tuning. It's sort of like Bayesian optimization approach, where we basically just try lots of things, see what works, and try to iterate on that. It's very expensive. It does kind of work. One thing we're hoping to move towards, and this is a very big topic now in machine learning space, are differentiable simulators. So we're not quite there yet, but kind of the stretch goal would be, instead of using like a Bayesian approach, can we just make the entire simulator differentiable end to end, and then we could actually try to infer these physical parameters through data using something like gradient descent. We're not quite there yet, but either way, what this does for us is we're able to take the simulator on a new building, take the historical data, and calibrate it and configure it in only a few hours, and now we have our simulation. So this is basically the full pipeline, and yeah, so where we want to go from here is live trials. So at Google, we are actually applying this to our own office buildings. Google has a suite of about 200 buildings. And so I'm very fortunate. I get to live in New York and play with buildings in Mountain View. And so that way, if I mess up, no one knows who I am. So very happy about that. But we're currently in live trials right now. And so far, we have initially promising results. We think we should be able to get between 8 to 15% reductions. It depends a lot, though, on the time of year. So winter, we can do a lot more. If it's already a temperate climate, not so much. And that's where we're hoping to move forward. I also want to add that another thing that we've been working on is trying to bring together people in both the buildings and the machine learning space, and just to get them to talk, which is kind of what's going on here. So I really love that. And hopefully that can continue, because I think there's a lot of miscommunication. Sometimes I'll talk to people in the AI space about this problem. They're like, what do you mean it's a solved problem? And then I'll talk to people in the building space, and they're like, none of the AI stuff works. And so definitely more communication is better. And yeah, that's what I have to say. Thank you very much.
We have time for.
We can go first. Yep.
Thank you so much. That was a great presentation and very, very clear. And I love how you spelled out the problem and talked about all these different options of your starting points. I was wondering if you looked into transfer learning and what you think of that. And what I mean maybe is, could you start with a model from a similar building as a starting point, even though it's not your building? And would that help shorten the time that you mentioned, like the reinforcement learning needs for training?
Yeah. Thank you. It's a great question, and definitely we have thought about it. And actually, one of the things that I have in the pipeline, we're trying to organize a contest on Kaggle. Kaggle, for those who don't know, is like a machine learning contest platform where basically we're providing contestants with data on 5 buildings, and we're trying to get them to build a model that transfers to 5 unseen buildings. So I think that's kind of exactly what you're proposing, a transfer learning paradigm. So that is hopefully launching on Kaggle. I hopefully with the $100,000 prize fund. We're still working out the details, but hopefully that'll be launching soon. I think it's definitely a very important step forward. I think our approach with the simulator is just one of many. I think the problem is very clear, but I think it's still not clear what the right approach is. So this is just one possible approach.
Oh, thank you for your great presentation. I just have, I think, two questions. I try to be quick. One is, I think you mentioned that you got 100-ish buildings with the Google, and I wonder, have you thought about maybe just extract all those features or building characteristics or even HVAC system, try to get some kind of like typical, conditions or archetype, or you can cluster them into different groups, and then you can develop, right, the reinforcement learning for each group, so you don't have to model, 100-ish building, because I think they share some common, or typical conditions together. And the second I have is, I think your goal is try to minimize the energy consumption, right?
Yeah.
So I don't know much about all of these buildings, but do you think like data center buildings are part of all those questions? Like you try to minimize the energy there? Because I think they wanted to make sure that your control would work and their data can be stored, securely and safely without any power outage, right? Then the data center cannot. So I just wanted to know more about, what specific buildings that you're dealing with, and do they include any data center? Because I think there's tons of energy used in data center buildings as well. Yeah.
Great question. Thank you so much. So to answer your first question, maybe I wasn't clear. At Google, we have a fleet of several hundred buildings, but that doesn't mean that we're starting with all of them. So right now we're focused on a core 2 or 3 that are all in Mountain View. We are thinking about obviously going beyond that. The problem is buildings tend to all be different, very different, right? So we have different devices, right? So sometimes we have this device to heat, sometimes we use that device to heat, and they're very different. So it's a huge challenge to get all the buildings to being like a common language. So we're starting small with 2 or 3. But we are eventually hoping to go beyond that. But your second question, right now, all the buildings that I personally am involved with are commercial. So none of them are data centers. I think there is another team at Google working on data centers, but that is not me. So.
Yeah, can take one quick.
Hello. Hi. Thank you for the presentation. So I'm an architect. I don't have that much technical knowledge. But looking at this flow, I have certain questions for your simulation. A, does it look into materiality of the structure?
Into what? Say that again?
Materiality of the structure, like different buildings will have different materials which have different heat index. So does the simulation also look at that? And does it also look at external factors of heat? Because I'm just reading this, I see it as it's like reading the layout and trying to do an internal understanding.
Yeah, so we don't consider that. Kind of what we're trying to do, and this is a very hard thing. I'm not saying we're doing it well, but we're trying very hard to build a system that can infer those properties from data. Because if we actually require you to specify all the material properties, this will never scale. Right? You're never going to be able to use this on 1,000 buildings. And so the goal is to actually have a system that explicitly does not consider those things, but then using data, try to infer them. And by the way, we actually might infer the wrong properties, but they just work, which is a whole nother interesting question. Maybe that's a philosophical question, but that is what we're trying to do.
Yeah, thank you. If you have further questions, we will have a discussion right now. So keep it, and thank you.
Thank
do
you.
that again. Thank you all again. So amazing presentations. It's amazing to see how we're using reinforcement learning, language model, language processing, all these cutting-edge AI technologies in solving, I think, different parts of the problem in the building environment. And the first question, I guess, a bit more on the occupant-focused part, where an interesting thing I've been thinking is so we're doing these experiments in lab settings, gather data, understanding, and to bridge that gap, to have those solutions in real buildings, real operations. Do average or normal occupants care? Do they have control? I guess, do they want control? Do we give them control? And really, a good way of combining the algorithm and these sites. Thoughts on that?
Yeah, I'll give just a quick thought. One thing that I've found when dealing with occupants is there's a very important balance between not making things very creepy. And so it really is important. So I found that if you are tracking everyone very closely, maybe the only exception is if it's their own home. Even then, if you track people very closely, you get very creeped out and unhappy. And so I think maybe a big consideration is like I don't know exactly where it's going to go. We have to make sure that we're not making people feel like their every motion and every act is being recorded, but at the same time still give them kind of the agency and autonomy to make decisions. I'm not exactly sure how to do that, but I think that's maybe a central consideration that's not often spoken about.
Yeah, I think my idea to that is sometimes we have to have the people as part of the loop. And sometimes we have to let the people outside the loop to let them be realizing inside the loop is really important. So I think like my whole idea behind that is we have to set up some kind of limitations to the controllability that we would give, because I think we love to control all this HVAC system that I could have. I can give you an example that my office at WPI, I can literally set up my temperature, but just I talked to the building manager and he told me that it never worked. But it gave me a very good feeling that I can control all the thermostat in my office, but it never worked when I talked to facility people after joining WPI for a couple of years. So I think that kind of trick, right, is it gives you psychologically a feeling that this could work, but it doesn't work, but you still feel like you control your office environments. I think that works, at least to me.
Just like the closed door button in the elevators. It never worked.
So yeah, I agree with that. If I can add something, I think from the literature, it is now kind of acknowledged that people do care to have control and not to be out of the loop completely. So complete automation probably is not what people really want. Or even in personalized comfort devices, it has been shown that if you have control, the benefits of the system is higher than if you don't. So maybe, I mean, that's my daily life, right? I really do care about humans, and that's why I want to give them agency to tell us what they want and how our buildings should be operated. My only concern is, should we push it to make them uncomfortable and then, okay, at that point we react, or should the building be automated before they are uncomfortable or unhealthy? So that maybe there should be a balance between people in the loop and out of the loop.
I'll give the audience a chance to ask. Yes. 1 second, I'll give you.
Hi, I'm also training as an architect, and so my question is more, I think, philosophical or looking at theory. So the sense of controlling your environment, I think, is also very particular to the culture here and to the West of trying to, like have as much freedom as possible, and then as much data, rationalizing, controlling your environment. And when I personally visited Japan, actually all the rooms, a lot of them have temperature control, like the bathroom have its own temperature and living room has its own temperature. And there's a different approach where it's more like a delegation and taking care of each other rather than the personal. So what I'm getting at is more that there's actually different approaches in different culture in how we manage our environment. And what was jarring to me actually was when I visited, there were a lot of very apparent architecture that were coming from the West that were influenced, that you could see the traditional architecture, and then I go into another more urbanized area, and this is obviously like a language that came from the United States or somewhere else. So I feel like with something like data-driven, optimized environment, it's very easy to also spread to the world, and at the same time, when we do that, we might be unintentionally superimposing a set of ideals, a set of cultural approaches. So I like that it was mentioned that it's very important to allow divergence, allow different kind of, I guess, breaking of the rules. And I wonder if you guys could, discuss this topic too.
Yeah, I can get started. I feel like to me, my ideas to your question is more like we should respect the personalization, right? We wanted to customize or understand the needs from very different individuals, and how can we really take that consideration into maybe architectural design at the very beginning and also into the HVAC system. So I think it's kind of like the trend in the field that we have the centralized HVAC system, but we have something that universally defined, but also how can we provide the flexibility and adaptability to each individual that might come up with very different requirements. And I think there's no one size fits all, but I think, like, to me, as we have to think about how to develop another personalized system which can modify or respect what they really need as part of this person might feel different or might prefer very different than the standards or the common threshold that we set up for the whole population. I think that's my solution or answer to your question, yeah.
Can I add something to that?
You want to add something?
Yeah. I'll just add briefly. I think the point that I ended on was there needs to be more communication between machine learning people and buildings people, but I think that equally applies. We need more communication among all different cultures as well. I recently went to a conference in Vancouver, and we were discussing these problems. I actually met a bunch of Japanese researchers working on this problem. And so it's great. I actually speak to them now every few weeks. And so it's actually, I think it's important to keep these conversations continued.
Thank you so much for all the presentations, and my question is actually close related to what you just mentioned. So, like, all of you work in like interdisciplinary fields, and architecture has its own kind of dialogue, and we have certain ways like that designers tend to use to talk. Then when you interact with engineers, architects, and other stakeholders, how do you do you have any tips on how to advocate for your projects, or how do you make designers care about this? Basically, how do you sell? Do you have any tips, and how did you deal with this kind of communications?
I can start maybe. My understanding, especially over the past years, is outside of academia, there is a lot of talk about money and how incentives and how do you make it happen through financing and all that. Because sometimes, especially when I talk about humans, practitioner thinks, oh, that's nice, but we have bigger problems to solve, right? So to make your point, sometimes I have to go back to the economic incentives and the problem, and that really touch many different people.
Yeah, my answer to that is pretty straightforward. I share my opinions to different stakeholders in very different way. So I would tailor down the focus of my presentation, whatever that I try to sell, to look at the person I'm talking about. If she or he really from architecture, then I would really talk about why X, Y, Z that I develop is so important to architecture design. If I'm selling it more for industry, right, then why my research of the technology or the models I'm developing could benefit your business or could attract more customers, or what I think everybody that they try to initiate a conversation, they have some kind of demands and needs. So if you understand what would be their demands and needs, and then you could tailor down or put different emphasis in your presentation, I think it's kind of a shortcut to me. Yeah.
I was once given the advice that science is 50% science and 50% communication. And that's kind of how I try to live. So I think if we're failing to communicate, we just need to do better. It's very important also to make sure that whenever we're communicating science, we never dumb things down, because people don't like that and they can tell. It's important to make sure that we communicate things. You can remove jargon, right? You can make things simpler. But it's always important, I think, to still tell the full picture.
I guess okay, there's one more question I think there. We can take that.
So my question is, speaking of the intelligent building control and optimized according to based on the human-central system. So I was thinking that, how do you think about the occupant speaking to the building system, or building system sensing the human sense?
You mean different types of responses or just really the voice?
Yes, I think maybe like more human to actively control the building, or building should automatically sensing what human need, and then they do some adjustment.
I think that falls back to the first question of human in the loop, of human out of the loop. Now there are a lot of groups working on wearables, for example, and how we can get information, or from infrared camera to get information about human physiology and control the building according to that. I still think that people would feel that that is automated, so it's not directly controlled by them. So maybe adding that and then some kind of control might satisfy the human craving of being in control of their environment.
Yeah, I think to me it's more like a two-way interaction. Like you wanted building to sense the occupancy, right? I think, to some cases or in some, control algorithm, it's better you understand the occupancy and how many people in this building. But on the other side, I think I don't know many of you, but I got experiences that I was stuck in the restroom and the lights are off, and I have to basically throw the toilet rolls to actually light up the lights, right? So I think there are so many, I would say awkward, embarrassed, situations that we hope the building sensors can be smarter enough to sense that we're here in these buildings, but I think it's never get enough intelligent to know what we're doing in the spaces. I think to me, we have both sensory system, we need people to take the active role, but we also need the buildings to sense the people as well. So I don't think one can override the other, and they should complement each other. Yeah.
Thanks. We can take one last very quick question.
That's a quick one. Yeah, thank you all. Quick one. So I think as an individual, what I found based on observation, that even with the thermostat at home or elsewhere, you would rather, as an individual, go and change your clothes rather than changing your own thermostat. And this is like a behavioral thing. So have you looked into that, and what's your thoughts about it?
So again, when I explain to people what I do, everyone has its own experience. And this is what I like to say is, this is your experience, but probably he will have a different experience. He will say, oh no, I always go and change the thermostat, right? So I think, as referring also to Nancy, what she said before, there is no one size fits all. Also in this case, also in occupant behavior and how do they interact with buildings. So we can try to find averages, but they're always going to be an outlier or somebody else behaving differently.
Yeah, so my idea to that is when I was a PhD student, I did something, as I showed, incentivize high performance people. So what we did is we tried to identify people who actually take the sustainable behaviors. We sense their office environments. We sense, how much they travel from, campus building A to B, and then they can get the reward token. If they adapt themselves through changing their clothes, if they got rewards points to 10, they can trade in with, the university with a free cup of coffee, or if you got 20 tokens, then you can get a free meal. So that's kind of the way that we can incentivize more faculty, staffs, and students to really think about how to take more sustainable behaviors, rather than just always looking at energy usage as the only way to adapt themselves to some of the conditions that they're not happy with. Yeah.
Yeah, I'll just add, I think it pays to kind of divide what you said into two scenarios. You have a residential building and a commercial building. So in a residential building, which I think is what you were talking about, it's actually easier often to, say, okay, this is what you like, this is what we're going to do. But in a commercial building, less so, although I think probably most people at work don't just have 5 pairs of clothes anyway, so it's probably less of a problem.
Yeah, I've seen it a lot in schools. So usually it's evident by like dropping my daughter to school. You see individuals wearing really basically winter clothes in summer, just because it is really damn cold inside. And you could identify it by even looking at the way they dressed.
But do they have access to a thermostat?
I don't think so.
Right.
All right. We're out of time, sorry. But I hope we had longer discussions for this. But overall, I think it's amazing presentations and amazing topics that I personally love it. It's very active in both academia and industry. It's a living example. That's how Google and other companies are doing, as well as in academia. And it's very interdisciplinary. I'm a mechanical engineer. There's architects, engineers, architects, designers. So yeah, thank you all, and thank you guys.